and I will switch the slide. Okay.
Great. Thank you very much, Chi, for the introduction. And hello, everyone. It's my pleasure to be with you this morning. And yeah, I'm pleased to be presenting this work on behalf of our research team that include Fuad Anur, George Skora, and Guoyan Wu from UC Riverside, as well as Stephen Sokolskis and Jordan Steen from CalSTAT. So my presentation today, I break it down to 6 sections. Okay, all right, it works now. So yeah, it is broken down to 6 sections, and then I will go through each of them one by one, starting with some background and introduction. And then we will look at state of off-road equipment electrification. Then we will kind of look at real-world activity and energy use of off-road equipment from our data collection. And after that, I will present the analysis of technical feasibility of electrifying off-road equipment. And lastly, review cost effectiveness and provide some conclusion and recommendations. So let's start with background and introduction. And this project was started back in 2019. And there was a delay due to the pandemic, and we finished the project at the end of last year. So yeah, I'm glad to be able to share the research result with you all today. And in terms of off-road emissions, so she already mentioned that off-road equipment contributes significantly to both greenhouse gas and criteria pollutant emissions inventories in California. And I borrowed this graph from the California Air Resources Board, and it was from, I believe, 2018. And back then, if you look at the NOx emissions in the state, we will see that most of the time for the past few decades, right, on-road heavy-duty vehicles have been the most significant source of NOx emission in California. But over time, their contribution has been decreasing, and it was projected that by 2021, off-road equipment would actually take over and became the biggest source of NOx emission in the state. I haven't had a chance to look back to see if that's the case, because now we are in 2022, so it would be interesting to see if that has been the case. And as you know, yeah, back in 2020, the California governor also signed executive order N7920 that was also mentioned by Xi. And that executive order mandated 100% zero emission vehicle sales of passenger cars by 2035. And along with that, the executive order also includes several other mandates. And the one that is applicable to our presentation today is the last one, where the executive order also mandate zero emission off-road equipment by 2035, with the caveat that where is feasible, right? And so we were in the middle of the project, and hopefully when this executive order was signed, so hopefully the research result from this project could help with the determination where it's feasible to electrify or go zero emission for off-road equipment. In terms of project goal and objectives, the overarching goal of the project is to look at different pathways for hybridizing or electrifying off-road equipment in order to maximize both climate and air quality benefits. And also, we want to make sure that these pathways are technically as well as economically feasible. In terms of specific objectives, there are 3 main ones. The first one is to characterize activities, duty cycles, and energy use of off-road equipment in the different applications, and then look at the trends towards hybridization and electrification in this sector. And lastly, determine off-road equipment types that could be partially or fully electrified now as well as in the future. I would like to kind of set the scope of the work that we perform. When we talk about off-road equipment, there are a variety of equipment that can be considered off-road, all the ways from cargo handling equipment to locomotive to ocean-going vessels. But in this study, the focus is only on two equipment categories, including construction and agricultural equipment. But even within these two categories, each of these two categories, there are still a variety of applications, sizes, and configuration of these equipments, as you can see in the graphic below. So one of the first things that we did is to reveal the different types of construction equipment and agricultural equipment and see which one should we focus on, right? On this slide, there are more than almost 20 types of construction equipment, and we will not be able to study them all. So we have to prioritize our efforts and focus on the one that are prevalent and also contribute significantly to both greenhouse gas and criteria pollutant emissions. And as we can see here, in terms of population, loaders, backhoes are the most populous in the state of California. And they also contribute significantly to CO2 emissions, rank number 2, as well as rank number 2 in terms of their contribution of NOx emission. So by looking at this kind of distribution, then we can identify the top contributors, types of construction equipment that we can focus on. The same is true for agricultural equipment. And even though tillers seem to be the most populous, but they are small and mostly they are attachment to the main tractors. So the major focus in this study is actually on the agricultural tractors, since this type contributes the most among all the agricultural equipment types in terms of both CO2 and NOx emissions. In the next section, I will provide our review of state of off-road equipment electrification. And I have to admit that it's changing so fast, right? In the past few years, we started the project back in 2019. And back then, there were already some equipment that have been electrified, right? Either partially as a hybrid electric or even full electric. So this is a quick summary of our findings. But in the final report, there is a lot more details and a lot more vehicle equipment types that have been electrified that we document based on our literature review. But back in 2009, as you can see on the slide, there are a few commercially available equipment that are in the form of, say, hybrid dozer or electric compact tractors. So for the full electric equipment, they tended to be small in size, and that's expected, right? Start with something small and then make it bigger as the technology mature. And around 2019, at that time, there were some prototypes that were being tested, like electric compact dozers or cable electric tractors. And then that just kind of showed the progression, right, from, say, a small electric compact tractor to electric tractor. And then now, 2022, there are electric tractors of large size already available. And that brings me to this slide, which is a few examples of a full electrification of large off-road equipment. So on the left one is electric dump truck that was tested in Europe a few years ago. Back then, it was the largest electric vehicle / equipment at the time. It was packed with 700 kilowatt hour of battery and utilizing 100 kilowatt charging station. And it used almost 600 kilowatt single motor, which was very impressive. But right around the same time, or maybe a little bit later, there was a demonstration at the Port of Long Beach of electric top handler that has 931 kilowatt hour of battery pack, utilizing 200 kilowatt charging station. So over time, just over a short period of time, we can see that the feasibility of electrifying large equipment is increasing very fast. And recently, there was a news release about battery electric tractors that have 1,000 kilowatt hour battery pack with 1 or 2 electric motors, right, at 500 kilowatt hour each. So it just goes to show what is the feasibility, the size of the equipment that can be electrified is increasing very, very fast. And from our review, we also identify advantages of electric off-road equipment as compared to their diesel counterparts. And there are many of them, right? So there are fewer moving parts. The electric motor has higher efficiency, and they consume, obviously, if it's fully electric, then they consume no fuel consumption. And one of the things that is kind of a little bit surprising and kind of not receiving a lot of attention is the amount of noise that is reduced, right? Electric equipment is a lot quieter than diesel equipment, and that is something that operators enjoy a lot. But there's still a lot of barriers to overcome in order to make electric equipment or zero emission equipment more prevalent. But each of these barriers, for each of these barriers, there are also potential solutions that can be used to overcome the barriers. The main one that is the first thing in a lot of people's mind is the short operating range. Because of the limitation in terms of how much battery can be packed onto the equipment. But as I showed in the previous few slides, that is very changing very fast. And then another one would be, another major one is the lacking in charging infrastructure. And that's not true only, that's true not only for the off-road sector, right? That is also a concern with on-road vehicle as well. And obviously, cost is still a major barrier. These electric version of the equipment are still much more expensive than the existing equipment, and there will need to be some incentive in order to help bridge the gap, the cost parity gap at this moment in time. Okay, in the next section, we will look at real-world activity and energy use of some of the equipment that we have collected data from. And based on our review of the contribution of these different equipment types to emissions in terms of CO2 and NOx, we targeted our data collection on specific equipment types. And in terms of construction equipment, these include tractor, loader, backhoe, grader, off-highway tractor, excavator, crawler tractor, rubber tire loader, and scraper. And for agricultural equipment, the only type that we collect data from is agricultural tractor. And for data collection, we use a small data logger that can be plugged into the ECU connector on the equipment, and the data logger read data of the engine of the equipment, and the data include a variety of things from RPM, fuel use, torque, and a variety of parameters. And the logger also have GPS receivers, so we can also synchronize the activity of the engine with the activity of the equipment in terms of how its movement change over time. And using the collected data, we were able to analyze a lot of statistics to help us understand the operating patterns of not only the equipment itself, but also the engine, right? So for example, if we look at number of engine starts and the amount of time that the equipment was idling, then yeah, we can kind of summarize the statistic and make comparison within the category as well as across the different equipment types. And yeah, this table may look a little bit busy, and yeah, it's available in the final report, but for today, let's just highlight, let's say, the statistic of idle. If we look at percent idle that each type of equipment does in their operating time, then we can see a variety of, I mean, we can see a lot of variation. For example, for crawler tractor, it's only idle for about 13% of its total operating time, whereas tractor, loaders, backhoe, it idle for almost 60%, 50-60% of its total operating time. So there's a variety of operating patterns with respect to different equipment type. The same is true for other types of statistics on this slide. There are power statistics related to power, work, and fuel consumption. And yeah, if we look at, for example, agricultural tractor, yeah, even for within the same type, right, the median power that the two tractors use are quite different depending on how they are used. And for grader, it's the same thing, whereas the first one in the group only use 19 horsepower most of the time, whereas the other one use almost twice or triple the amount of power for the majority of the time. And because of the variation in the activity patterns that we observe, yeah, it just raised the question, how are these real-world activity for the engines, right? Different from what the engine certification cycle look like. And as you know, for certification cycle of off-road engines, there are two main ones: the non-road steady cycle, or we shorten for NRSC, and non-road transient cycle, or NRTC. And we plot the distribution of percent torque operated by the engines of the equipment that we collected data from, and compare them with the percent torque distribution of these certification cycles. So as you can see, the certification cycles are on the top rows. And if we look at the color pattern overall, we see that the real world pattern of torque distribution is quite different from what the distribution of certification cycles look like. For in the real world, most of the equipment has the most operating torque around 5%, 5 to 10%, and that's not reflected in the certification cycles. And this just go to show that the current certification cycles may not be representative of real-world operating pattern of the engines. And that's something that to keep in mind when we look at the impact or implication on emissions from these equipment. This slide shows details distribution of real-world data in terms of torque and engine speed joy distribution as compared to the joy distribution of the certification cycle. And again, yeah, when we look at the histogram, let's say for the engine speed, as well as for the torque, we see that the two histograms here are quite different from each other. In the next section, yeah, I will talk about the technical feasibility of electrifying some of these off-road equipment and see which one can be electrified and which one still need more development. First of all, using the data that we collected in the real world, we were able to obtain or estimate the torque and power from the requirements from the equipment on a second-by-second basis. And then we analyze the second-by-second data, look at their distribution, and can derive these two plots, right, which show equipment-specific torque and power distribution. And we use the maximum values as the requirement that can be compared against the current motor ratings of commercially available motor. And we use the upper adjacent values to compare with the continuous rating. And by that, so based on the distribution that I showed in the previous slide, we are able to summarize the values, the maximum value and upper adjacent values for each of the equipment that we have data for. So for example, for torque demand, the maximum value for agricultural tractor is 416 Newton meter, and the upper adjacent value is 232 Newton meter. And that can be compared to the torque ratings of commercially available electric motor at that time, and see whether some of these commercially available motors would be able to fulfill those torque demand. The same exercise was done for power demand, where we compare the maximum and upper adjacent values of power demand against the peak and continuous rating, power rating of the electric motors. And after that cross comparison, then we can identify for each piece of equipment, and based on their real world torque and power demand, are there electric motor out there that are already commercially available that can be used to operate these equipment. And on this slide, we can see that for all of the equipment that we collect data from, all of them has at least one commercially available electric motors that can fulfill the torque and power demand of the equipment, except for the two off-highway tractors. Their torque and power demand are larger than what electric motors at that time can perform. But this is for one electric motor, so it's possible that a multi-motor setup can still provide enough torque and power to fulfill the torque and power demands of these two off-highway tractors. So that part was the motor sizing analysis, just to determine whether there is a motor that can work with these electric equipment. For the next few slides, we will look at battery sizing analysis to determine whether we can have electric equipment with enough battery size to perform the work that the equipment does in a typical day. And in order to do that, we have the torque and power data from the equipment that we collected, but to translate that into the amount of power and energy required by the electric motor, we have to account for the efficiency of the electric motor. So we utilize an efficiency map of one commercial heavy-duty electric motor, as shown on the left side. And then based on this map, then we derive maximum and minimum efficiency operation as a function of motor torque. Because we have the torque data, and because the efficiency at a torque, a single value of torque can vary based on the motor speed. So we create these two boundaries to indicate for a specific torque values, what is the range of efficiency from maximum to minimum. And in our analysis, we use the minimum efficiency operation as the assumption, because that will be more conservative, so that we can ensure that even if the motor operates mostly at the minimum efficiency level, the battery that is sized will still be able to supply enough energy to keep the equipment operate throughout the day. Okay, in terms of the calculation, so I mentioned earlier, we use the motor power demand that was based on the data that we collected, divided by the minimum motor efficiency at the specific torque value, and that will give us the instantaneous energy consumption on a second-by-second basis. And then we sum the second-by-second energy consumption across calendar days, and that will give us kilowatt hour of energy for each of the operating days that we have data for. And then we have these values for multiple days that we collected data for. Then we identify the day that the equipment used the most energy. So that is the threshold that we use to determine what we call usable battery size. It means that we have to size the battery for this equipment enough to fulfill the most demanding day in terms of energy requirement. But because for battery, there is a possibility of deep discharge, so we want to prevent that. In order to do that, we add 30% on top of the usable battery size to result in what we call equipped battery size. This is the total size that will be put on the equipment in production. And this slide shows the summary results. Again, there are multiple sizes here because we go from usable battery size that is based on the daily energy demand, the maximum daily energy demand for the equipment, and then we add 30% to result in what the actual battery size that need to be put on the equipment, and then we also round it up in order to make it more make it easier to package the battery. And we use these values, the rounded equipped battery size, we use this last value to compare against a benchmark, right? And if you remember one of the earlier slides today, in real world, there is a 1,000 kilowatt hour electric tractor that is already operating or being tested. So we use 1,000 kilowatt hour as a benchmark and say, okay, if the required battery size is less than that, that means it's probably feasible to electrify that specific equipment. And based on that benchmark, we can see that for most of the equipment types that we have data for, they can be fully electrified because the required battery size is less than 1,000 kilowatt hour. The only two exceptions are off-highway tractor and scraper. And these may be the categories that need to be hybridized for the time being before they may be able to fully electrify in the future. Now, the analysis so far is based on the assumption that we know the amount of energy required for each day, and that the battery is sized such that even the most demanding day can be fulfilled. However, with electric equipment, we also have to take into account the charging, because unlike diesel equipment, which can be refilled very quickly, to charge electric equipment with the current technology, it may take a long time. And that's one of the limitations now. So we perform a simulation of activity and energy flow in a time series format and see how many days the electric equipment would be able to actually perform the same work as diesel equipment. And in order to do that, basically we run a simulation on a second-by-second basis and can simulate the electric equipment being put through the same energy demand profile on each day. And once the operating day ends, once there is a gap when the equipment is not being used, that's when we make some assumption regarding charging. For example, at the end of the shift, then the electric equipment would be charged at the site, right? And that could be 6 hours, 8 hours, or 10 hours, depending on what the data imply. Aside from end-of-shift charging, we also look at opportunity charging, where there is long break, and long break here, I mean longer than 2 hours. So we assume that if the operator will have at least 2 hours of break, that break can be used as the opportunity to charge the electric equipment if there is charging infrastructure on site. We also simulate the different charging power levels that would be required in order to ensure that the electric equipment would be able to perform all the work that diesel equipment does. And as you can see on this slide, these plots, I kind of call them diary plot, because it's kind of follow the equipment operation on the day-to-day basis over time. And this is simulated electric scraper. On the left-hand side, if we use 50 kilowatt charger, which is a common DC fast charger nowadays, then there will be many days that the electric scraper would run out of battery before the end of the shift. And that's because 50 kilowatt charger is not enough to charge up the equipment to 100% before the start of the new shift, right, the next day. And this is like, despite the overnight charging, like from 7 p.m. to 7 a.m., that's 12 hours. That's still not enough because the scraper is so big, the battery size is so large. So for this scraper, then a 150 kilowatt charger will be needed, and that will allow the overnight charging to be able to top off the battery to 100% before the next operating day. And doing that analysis for all the equipment in our data set, we can summarize that. I'm sorry again for the busy table, but the takeaway from this table is that for most of the equipment, because of their operating pattern, which normally operating only during the daytime and have a long time at night that can be used for overnight charging. So for most of them, a 50 kilowatt charger would be enough. The only few exceptions are, again, the big off-highway tractors that have a really large battery size, as well as the scraper. So these equipment, because of their large battery size, a 50 kilowatt charger wouldn't be enough to charge them up over the 10, 12 hours overnight charging, and a high power level would be needed. Okay, in the next section, so far we now have determined which types of equipment can technically be electrified, right, based on the size of the motor and the size of the battery. Now, we will look at the cost effectiveness of electrifying off-road equipment, because again, one of the major barriers of electrifying this equipment and deploying this equipment is the cost, right? The capital cost that fleet operators will need to invest to purchase this electric equipment right now would be much higher than the existing type of technology. So in this cost effectiveness analysis, if an incentive program is to be designed in order to encourage the transition to electric equipment, where should we invest those incentive dollars first? And to do this analysis, we use data from California Resources Board off-road inventory model called Offload 2017. And Offload 2017 contain data regarding the population, activity, fuel consumption, and emission for all off-road equipment types in California. So in this analysis, we go beyond just the 6-7 types that was part of the previous analysis based on real-world data. This is, we look at all the equipment types under the construction and agricultural categories. And we assume that in order to determine the cost difference between electric equipment versus diesel equipment, we assume that the electric equipment will take, basically will be, some of the components will be a drop-in replacement of the ICE or internal combustion engine components. For example, in the diesel version, the main components are the engine and fuel tank, which if this equipment is to be turned into electric equipment, these two components will be removed and then replaced by motor and battery. And then another assumption that we make is, if this electric equipment is funded through incentive dollar, then they will be used at the level of activity for the calendar year that it is purchased. Just to explain this assumption a little bit in more detail. For example, if a fleet operator take an old diesel equipment, maybe 10, 20 years old, and then apply for incentive dollar in order to scrap that old diesel equipment and buy a new electric equipment that replace it, it's most likely that the new electric equipment will become the main equipment of that operator, right? So the usage will be much higher than the old one that maybe not being used as much because of its being old. Okay, so in terms of now we I have explained the basic assumption. Now, before we can calculate the cost of each component, we have to size the component first, right? We have to know for each type of equipment, what would be the motor size, what would be the size of the battery, and what would be the typical size of the diesel engine on the equipment. Now, we don't have real-world data for all types of equipment in the Offload 2010 database. So what we have to do is to estimate the sizes of these components based on the data from Offload 2017 that we have. And let's start with battery. To estimate the size of battery of a specific equipment, we use the fuel consumption values from the Offload 2016 database and take the maximum values across the different model year, and then convert it from gallons per day into kilowatt hour. And then we assume that the battery will go to replace the diesel engine, and I'm sorry, the battery will go to replace the fuel tank, and the amount of the size of battery that would be required would be equal to the amount of diesel fuel that is consumed, and then multiplied by engine efficiency and divided by motor efficiency. This is to do energy conversion, and that will result in the battery size required to be able to supply the same amount of power to the equipment. For motor, it's a simple conversion from horsepower to kilowatt, and the same for the internal combustion engine is a simple conversion as well. Now, once we know the size of each component in the analysis, then the cost is basically a multiplication of the size by the per unit cost. And I have a plot that shows what is the per unit battery cost or per unit motor cost from a source later. But basically, for the electric equipment, the cost include battery cost, motor cost. We also add additional EV system costs, because to build electric equipment, there could be additional electrical system that were not there when it was diesel, right? And then, yeah, we also have to account for this cost, and we account for it as a function of the size of the motor. And on top of that, because the new technology usually costs more to develop because of the research and development engineering requirements and all that. So we also add additional advanced engineering costs to the total cost of the EV version. For diesel equipment, so the main one is the cost of the internal combustion engine, which is a function of the size of the engine multiplied by per unit cost of that engine. And then for fuel tank, based on the literature review, we found a value that represents the typical cost of a fuel tank. And once we know the cost of the electric equipment components and the cost of the diesel equipment components, the required funding amount basically is just the difference between the two. And that is the gap that incentive dollars can help fill in order to make the purchase cost for the operator to be about the same as they would purchase diesel equipment. So that is the required funding amount. And in terms of emission reduction, that can be achieved by turning over from diesel to electric equipment. That is data that is already available in the Offload 2017 database. Now, one assumption that we made is for a typical off-road equipment, they are operated not 24/7, so there will be a lot of days that they were not used. And based on analysis of real-world data, we found that typically they are operated 186 days a year. And so the emission reduction on an annual basis is then just simply a multiplication of emission produced in tons per day and multiplied by 186. And once we have these two calculated, then we can calculate the cost effectiveness by accounting for capital recovery factor or in other words, the discount rate, right? And we assume discount rate of 1%. So we apply this calculation to all equipment types, and we first have to make assumption regarding the base case because there's many parameters involved. And these assumptions include 25% efficiency for diesel engine, 72% efficiency for electric motor, and the advanced engineering cost that I talked about earlier, we assume to be 10% of the total cost. And then I already mentioned the discount rate to be 1%. And the next assumption is the per unit component cost. This is very important. So we obtain these data from literature, and I have the sources cited below at the bottom of the slide. And the data from these sources provide these data points, these discrete data points. So for example, for battery, the dollars per kilowatt hour price, there are 4 data points provided in the report. And so we plot these 4 and then fit a curve through the data points in order to be able to get an estimated price for each calendar year. And we apply the same technique to the other component costs so that we can estimate the component cost, the per unit components cost for every calendar year in our analysis. And this is an example of the cost effectiveness results. The top one is the dollars per ton of CO2 reduction. The middle one is dollars per ton of NOx emission reduction. And the last one is dollar per ton of PM2.5 emission reduction. And we separate them out because for each type, model year, and calendar year of equipment, the amount of emission reduction vary, right? One thing that we can observe is the color pattern between CO2 versus the criteria pollutant. Basically, they are almost opposite to each other. And that's because for new equipment, newer diesel equipment, they tend to be used more. So they have a lot more activity. And that means they consume a lot more fuel and produce more CO2. On the other hand, the new model year equipment, new model year diesel equipment, they tend to be cleaner, right? Because they meet tier 4 standard or tier 3 standard. And because of that, the amount of NOx and PM2.5 emissions from these newer equipment are not as high as the older ones. And that's why the cost effectiveness seems to be going in the opposite direction when we talk about CO2 versus criteria pollutants. Now, we have the results for all types of equipment on also all sizes. And that allows us to make comparison. For example, if we want to look at excavator, so the top one is the cost effectiveness for excavator in the 175 horsepower bin. And the middle one is the cost effectiveness of excavator 100 horsepower bin. And we can see that they are very similar in terms of pattern. But if we look at some area, there seem to be some differences in the model years 2002 to 2009. So having this information allows us to kind of customize the funding program to a specific model year. We can target the ones that would be the most cost effective in terms of incentive dollars. The same is true where we can compare not only within the same type but also across different types, right? So here it would be, if we compare the top one and the bottom one, excavator and graders, again, the color patterns seem to be similar, but if we look at the scale on the right-hand side, the excavator is much more cost-effective because the scale is in the $1,000 per ton range as compared to graders, which is 2 times or 3 times more expensive. We also conducted sensitivity analysis because, again, we had to make a lot of assumptions, and we start with one set of base assumption. So we conducted sensitivity analysis to see if some of these assumptions change or differ from what we assume, what would be the impact on the cost effectiveness. And so for each of the 10 parameters, aside from the base value, we also simulate the cost effectiveness with 3 additional values, or 2 additional values for each. So in all, we simulate almost 6,000 scenarios, and that result in a range of cost effectiveness, right? So what we see here is the cost effectiveness. The blue lines are the mean, and then the red lines are the mean plus 1 and minus 1 standard deviation. And this is cost effectiveness for each calendar year and model year for excavator, 175 horsepower bit. So yeah, one thing that can be noticed right away is how, if you look at the top one, how cost effectiveness kind of decline over time. So as the technology mature, the battery getting cheaper, it's more increasingly more cost effective to be able to reduce CO2 emissions by going electric. Now, we have done that for, again, all equipment types, all size, all calendar years and model year combination. That's at the micro level. Now, if we sum the result up into a macro level and look at it from the type and size distribution, then we can see that if we want to design an incentive program that target certain types of equipment and maybe certain sizes, what would be the most effective? And the results show that if you look at, it doesn't matter if it's CO2, if it's NOx or PM, it's most cost effective to fund a turnover of equipment in the 51 to 75 horsepower range, because that's all green. And then across the 5 equipment type that we have analyzed here, the ones that is most cost effective to be electrified is the tractors, loaders, backhoes. One thing that I like to point out is the numbers that you see in the previous few slides in terms of dollars per ton reduction of emission. Those numbers may seem high because the cost assumption that we use were fairly old. Is from one of the literature several years ago. And when we look back to recent data, especially on the battery prices, they have dropped significantly over the past 5-10 years. In fact, yeah, if we look at this plot, the average price of battery pack have dropped almost a half, right, in 2020 as compared to, I'm sorry, not drop almost a half, but I mean the actual price in 2020 is just only about a half or 60% of what our assumption projected. So in reality, the actual cost effectiveness number would be just about half of the numbers shown in the report. All right, so I think we are almost an hour, so I will kind of go through key takeaways quickly, and then we can go to Q&A. The first thing is it's amazing how the landscape is changing so fast. During the course of the project, I often get emails from friends and colleagues about new releases of electric equipment. There seem to be new models or new types of equipment that have been electrified and will be commercially available. So it's just amazing how the technology is changing so fast. But that is mostly on the vehicle side. There's still a lot of work to be done in terms of the infrastructure side, in terms of how we can make sure that these equipment, when they operate it out in the middle of nowhere, they still can access charging station. There's still barriers regarding cost and how we can bridge the gap between the electric equipment cost versus the existing diesel equipment cost, and a lot more things to work on in the next several years. But this is very promising. And based on the real world data that we collected from selected equipment types, we can see that there's a wide variety of energy use, activity patterns, not only within the equipment type, but more so across different equipment types. And so no one size fit all, and we have to be mindful when we try to understand the implication of emissions from certain equipment types, or how to design specific equipment types for the electrification. And then in terms of the technical feasibility of electric off-road equipment, based on the analysis conducted in this study, there are many types that could operate with a single electric motor. And then most of them can also be fully electrified now with current battery technology, coupled with just a typical DC fast charger of 50 kilowatt. Aside from off-road tractors and scrapers, the other categories that are shown on the plot to the right are ready to be fully electrified. And in terms of cost effectiveness of electrifying this off-road equipment, again, it's generally more cost effective to electrify the equipment with smaller in size than 100 horsepower. And the dollar per tons of emission reduction today would be about half of the results shown in the report and on this slide, because battery prices have dropped so much over the past several years. So recommendations, based on what we have found, it makes sense to initially focus on the most popular and top emitting equipment types. And these include agricultural tractors, excavator, graders, rubber tire loaders, and tractor loaders backhoes. And in a similar way, it makes sense to initially focus on equipment with 100 horsepower or lower to begin with. First of all, these equipment account for about 78% of the total population of off-road equipment in California, and also about a quarter of diesel fuel consumption. And on top of that, it's relatively more cost-effective to electrify these small equipment than the larger ones. So dream big, but start small. And I would like to acknowledge California Air Resources Board for the funding support for this study, and for the program support from Sung Ju Yoon, Harikishan Perugu, Sonia Collier, and Chi Yao. And many thanks go to CARC program staff for feedback and comments during the course of the project. I would also like to acknowledge Tom Durbin and Chas Frederickson of CSET UC Riverside for their contribution to this study. And also thank you all the fleet operators and interviewees for participating in this project. Thank you very much for your attention. My email address is on the slide if you have question later on, but I think we can go to the Q&A from the chat box.
Great, thank you so much, Dr. Bo-Thompson. So now I will go over the chat box from the top to the bottom. And as I mentioned earlier, that you can always raise your hand and I will unmute you so you can ask a question yourself. Yes, the slides will be shared and presentation. The audio and video will be shared at the same site that I presented in the introduction slide. So the first question is from Matthew Mayer. Are you basing this on the rating of the engine or the actuals from the small sample of one tractor? I'm not sure which one is he referring to.
Yeah, this question came in earlier, so it might,
probably earlier. Yeah,
the real world analysis.
yeah, it's probably.
Yeah, I could ask the question if you guys allow it.
Yeah, go ahead.
I was just sorry, Matt Meyer with Cal Portland. I'm not sure if you're familiar with us or not. We're a big materials producer on the West Coast. My question was, you're talking about replacing a diesel engine with a battery pack and electric motor, and it looked like you were basing your numbers on the actual usage of the sample you did. For example, that one tractor had quite a bit of idle time. Are you actually looking at the rating on the engine from the manufacturer, or are you looking at what your small sample produced, was the question on replacement. So if we're talking about a 100 horsepower engine, but it only worked 70% of the time and never used the full 100 horsepower, are you recommending a 70 horsepower electric motor? Or are we talking apples to apples, 100 horsepower to 100 horsepower?
Yeah, that's a good question, Matt. Thank you for this question. So in the analysis, we base our analysis on the data that came off the engine. So yeah, to reply to your last part, yeah, if it's rated at 100 horsepower, but yeah, actually it's being used as just 70 horsepower. Yeah, the analysis will be based on the 70 horsepower requirement as evidenced by the data. And I like to also point out that the analysis here has some limitation, right? Because the real world data analysis, we only have just a few equipment for each equipment type in our data set. So they may not be representative of population of that particular equipment type.
Can I ask a follow-up on that same question?
Go ahead.
So it looked, if I remember the slide correctly, it looked like you had a box plot. So even if it, say, operated at 70 horsepower peak, you didn't go to the top of the box plot, you picked a certain level below that, or did I misunderstand that?
Yeah, so in this box plot, so we use both the peak values, which is the maximum point in the box plot, as well as what is called the upper adjacent values here. So the maximum values is compared against the peak rating, and the upper adjacent is compared against the continuous rating.
I guess my point was, it looked like there was a statistical analysis that there was, say, 95% of the time was operating below here, so we use that as the equivalence point, as opposed to 100% of the time. If you pick the absolute peak, right, then it's going to be higher. And so, was it the absolute peak or not? And if not, then that means that however it actually got used, it wouldn't be able to do that with the smaller battery size.
It's based on absolute peak. Yes. In terms of are you referring to motor sizing or battery sizing?
So you mentioned it was based on actual operation, and the previous commenter saying, well, okay, say it's a 100 horsepower tractor and it only operated to a peak of 70 horsepower. Did you use the 70? And you said it was the 70. And I was saying, okay, it looked like there was a statistical box plot, and that the top of that plot was not being used, that it was the top of the box, or some 90 or 95% range, and that's what I was asking about.
Oh, so we use the top of the box plot. So for example, for motor, we make sure that the maximum motor, the maximum torque required or maximum power required by the data, shown by the data, is below the rating, the peak rating of the available motor.
Okay, thank you.
Great. Let's move on to the next question. So I'm going to go over some early questions in the chat, and then I will go to the hands raised. Yes, the link will be provided. I can show the intro slides later after all the questions. And then the presentation or the final report has not been uploaded yet, so they will be available next week. So the next question is, for a scraper, are you looking at the total for both engines on the scraper or just one of the other? I think it's really similar to the previous question. Yeah.
Right. Yeah. For scraper is tricky. So we have access to only one ECU connector, and whatever is report on that data channel is what we use, and we didn't have knowledge whether that is based on just one engine or both engine.
I can help answer that for you. It was a single engine scraper is what you showed.
Mm-hmm.
All right. So next one is, do you have any research on TRUs, transportation refrigeration units? They are considered as off-road equipment, and this person would love to have some data information on that.
Yeah, TRUs are not in the scope of this study. Yeah, I'm not sure if CARB may have other study that look at TRU specifically.
Well, so in my knowledge, we have not had any research on TRUs in electrification yet, but I will keep that in mind and then reflect that to my colleagues. So the next one is also from Matthew Mayer, and is there a question here? Matthew, do you want to elaborate it yourself?
Yeah, it was just more of a, looking at what you guys presented, you have loaders and backhoes. We're really familiar with the industry, and the scraper you guys did the analysis on is more of a utility scraper, not a production scraper. I guess I just caution trying to generalize off-road equipment with what you guys are looking at, because it's such a small little snippet of reality of utility equipment versus what we run as production equipment. So like, for example, one of these little scrapers, we might run 1,000 hours out of the year, if that, but you'll go to one of my main lines and we're running 6,000 hours a year. It's 2 shifts, 4 hours in between shifts just to lube them and fuel them and get them back in, because it's a 24-hour operation. We've dealt with this on the on-road side, so Just a lot of it doesn't make sense to me, and I kind of continue, and I apologize for all the comments and questions. It's just you got to really look at the whole picture, and you'll hear in a lot of presentations cradle to grave, cradle to grave or cradle to grave, looking at full life cycles, looking at full production cycles. Yeah, we can say we're reducing a bunch of emissions here, but if you actually look at the emissions of whatever tool it is to generate the electricity, is that calculated in this for actual CO2 and NOx reductions, the processing of the batteries, all those, people are missing that portion of this, thinking we're doing a big reduction in CO2, but you actually look at what it is to produce a battery, to charge a battery, there's a big loss in it. And we're actually going backwards in some people's opinions. I just caution look at the whole picture of it. We run these hybrid large tractors like 988Ks, and they cost a lot more money to run than a regular power shift machine, because you can't rebuild a lot of these electrical components. So for example, a large battery or a large electric motor in one of these 988s, I normally can rebuild the engine at 30,000 hours. I got to replace the whole motor for $250,000 instead of being able to rebuild it for $40,000. So I just, say, look at the whole big picture. There's a lot of us out there that are willing to share information, and we converted our whole ready mix fleet to natural gas and used renewable natural gas because it made more sense for everybody and for the environment. So I'll get off my soapbox.
Thank you for the comments. So it's very true, your comments, and this kind of study is one of a kind, and it's very pioneer even for CARB. So that's why we have really limited resources, and we can't really test a large amount of different kind of tractors or we would like to. But Kinok, do you have anything to add to this comment or?
Yeah, thank you for sharing that insight. And yeah, I agree. Right now, we are very limited to just this set of equipment that we collected data from. And yeah, we would have loved to expand the data collection and analysis effort to cover a larger population. And yeah, I also see your comment about the cradle to grave or life cycle analysis. And yeah, that's one of the things that we discussed towards the end of the project, as well as potentially something to look at in the future. So yeah, all these are good comments.
Right. And also just as information about FYI for everyone that the slides, the presentation, and also the audio and video will be available online. And at the end of the question session, I will show the slide again to show everyone the link that you can access to the presentation and the final report on the CARB website next week. So let's move on to the next question by Danielle. By dropping in, are you meaning you assumed did not account for costs associated with redesigning the equipment?
Yeah, we do account for that. And yeah, I'm trying to get to that slide. So we have assumption regarding, what is called advanced engineering costs that basically cover the R&D towards the redesign of the powertrain.
Right. So the next question is, did the estimated cost match with the year 2020 actual cost?
Yes, this is interesting. It did not match. And yeah, we used data from the literature that we found at the time of the study. And as that's the one. And as I mentioned, the projected value of battery price is actually much more higher than the real price. So the real price is just about 60% of the projected value. So the numbers in terms of cost effectiveness are like overestimated. So it should be a lot cheaper, like by half.
So the next question is, it looks like we're not looking the fuel cycle of event. What NOx and CO2 is used to produce the energy to charge the equipment? It sounds more like a comment. So
Right. Yeah. I think this go back to
yeah.
the life cycle analysis. But I think yeah, especially for CO2, I think at least in California, the source of our fuel, our electricity is getting cleaner and cleaner, right? We have at least 40% renewable in our electricity mix. So hopefully that will help with this concern.
Right. So the next one is in relation to the cost of a battery kilowatt each chart, the costs were projected to 2030 from 2015.
That's correct.
Right.
Yeah, it was the source of data that we had, and yeah, we used 4 data points to do interpolation and as well as extrapolate it out.
Okay, the next question is, why would we look at any equipment older than 2008 to 2010, since most fleet have purchased out to tier 2 and older engines already being compliant?
It's just because there are still some equipment that are very old. So this is reflected in the Offload 2010 database. There are a few equipment that are still in, at least in the database. So yeah, we kind of cover all the way.
All right. The next question is, where are you getting your battery pack cost from? Are they specific for lower volume off-road equipment application or from highway vehicle? Sorry, I didn't finish the question.
Yeah, so it's from, oops, yeah, it's from, yes, it's from this source, these two sources. And we use these two sources because it's comprehensive in the sense that it provides not only battery price, but also the per unit cost for electric motor and additional EV system cost. But yeah, it's fairly old. So yeah, like I mentioned earlier, the cost may have come down a lot as evidenced by the price of the battery.
Canuck, you know, my comment about battery pricing is that, you know, you really have to be able to drive volume to get to the battery prices that are talked about so often, you know, either in general terms or, you know, specific to the auto industry. Even amongst the car companies, they have different specific costs. And here with off-road, one of the challenges will be, you know, with such fragmented manufacturing, low volume of equipment, either the costs are going to come down from standardization, but it's not clear that they can drive their costs down like you can in automotive. It's just they don't have the volume to be able to get those supply chain cost reductions and the volume of everything from, you know, from critical minerals right through to, you know, to final packs, because these packs aren't going to come out of cars. They're going to be designed specifically to go on these machines. So I just caution that this is something that actually needs more investigation, because carrying costs over without doing a full supply chain analysis of what's driving the cost is going to lead to an inaccurate answer.
Yeah, thank you, Kevin. Yeah, that's a very good point. Yeah, the market for battery will change a lot, right? With now a lot of attention on EVs, and lithium seems to be yeah, something that people seek after. And yeah, that's a very good point. Well taken.
Yeah, thanks, Kevin.
Questions for me too. So, you know, I've experienced in my own career construction equipment, farm equipment that can be used heavily for periods of time and then not used at all for many months. And sometimes in the construction, even more than a year or more at a time. And then, you know, the right project comes along that those machines are needed again, and they will get torn down and totally rebuilt and go into that project because that project is worth so much money. As we store equipment with batteries, there does become other implications of storing, you know, batteries for a long period of time. And there are potentially other uses that those batteries might be redeployed to, whether it's just storage, but again, it brings in another cost, you know, if one wants to try to do this. So, you know, the standardization is used and batteries can be redeployed to something else, or machines can be plugged in and served to do something else to try to offset their cost. But most importantly, a battery lives long when it's cycled. If it's held at one charge level for long periods of time, it doesn't like that.
Mm-hmm. Yes, yeah, that's good point too. Yeah, I think there's quite an interesting development in terms of vehicle to grid. So there may be a room for electric equipment that is not being used for a period of time to provide power back to the grid or to power other types of vehicles. So that's interesting.
I guess I just wanted to follow up on what a couple of people have said now about the assumptions about the activity. I mean, you mentioned relying on Offload 2017, and I know that's I think there's an Offload 2021 right now, but I mean, I don't think it's that different. It's just that the way that those models calculate things, they do not take into account the type of variability that I think Matt was mentioning. They assume that the load factor is the same for a certain equipment type, regardless of which size you're talking about, across the entire size range. They assume that the hours per year is the same for a given type of equipment across the entire size range. And, for the purposes of what they were, using it for, to just come up with a total off-road emissions inventory might have worked, but as far as actually looking at the actual variability out there, it definitely will miss that.
Totally agreed. And yeah, we see that too in the real world data that we collected from a small sample of off-road equipment. Yeah, within the project it's just that, yeah, we don't have resources to be able to reflect all those vulnerabilities. But one thing that can be done is when we look at the, say, cost effectiveness calculation. So this is just a framework, basically set up a framework in terms of how the cost effectiveness values can be derived. But a lot of these assumptions can be changed. They can be customized to specific application or even specific operators.
So a lot of people were asking the online source. So you can find the online website here, and I will put into the chat box, just in case anyone wants to leave early. So you can find this presentation and also the slides here, but it will not be uploaded until next week, just for everyone's information. All right, so let's go back to the question. So the next question is from, I think it's also from Kevin, but I think we sort of answered that one. So I'm going to skip that. So the next one is from Adam. Could you quickly go over again the cost effectiveness calculation? Specifically, there is a discount rate and project duration that goes into the calculation. What are those and what was the assumption?
Sure. I try to go to that slide. Okay. So yeah, in order to do the calculation, we have to assume a project life. And this represent, for example, the life of the equipment that will receive the incentive funding. And typically for off-road equipment, is assumed to be 10 years. So here project life is 10 years, or project duration in the equation is 10 years. And the discount rate is just to reflect the fact that the value of dollars change over time. And it can be thought of as the inflation rate, if you will. I know it's assumed to be 1% because a few years ago, the interest rate was really low, and now that probably has to be updated.
Hope that answered the question. So we can move to the next one from Colin. So how representative do we think the use of those equipment are? Most equipment only run a few hours per day on average. For example, the tractors only appear to have run about 3 hours on a max day. Have people familiar with the practical use of this equipment evaluated their use? And if so, who are they? Similarly, have people familiar with operation evaluated the practical aspects of getting those equipment back to the charging station or equipping rural areas with charging infrastructure?
Yes, so yeah, I think the question of representativeness of the data used in the analysis is a big one for sure. Yeah, I cannot say that the data that we collected from this small set of equipment sample would be representative. And yeah, more data will certainly be needed. And yeah, I think there are already many comments from us here that point to the variation of how different equipment types are operated in the real world, and not just by equipment type, right? Even by operators. The same equipment type used in Northern California for one type of construction could be quite different from another construction project in the Central Valley and things like that. So yeah, this analysis is not meant to be like a definitive answer that yes or no, or it should be this size. Yeah, it is kind of more like the first attempt at looking at the potential feasibility of electrifying some of these equipment. And then with regards to charging station, that's really good point, Colin. And also I also received direct message from Erich, I think, asking about the same question. How can we supply charging to construction and agricultural equipment that operate out maybe in the middle of nowhere with no grid infrastructure? And that's going to be one of very, very big barriers for electrifying this sector. But yeah, there are some potential solutions. For example, mobile chargers, mobile trailers that carry batteries and charging ports that can be used to charge this equipment, similar to the wet fueling that is being used with diesel equipment nowadays.
Thank you. Colin, you have a follow-up?
Yeah, if I
question.
can just expand on
Yeah.
that. I mean, if we know that we have equipment that is massively underrepresented, right? Like if we're looking at a tractor that at most runs 3 hours a day, right? That's like not close to reality. So I mean, couldn't we like look at less precise measurements and then scale things? So if we know that equipment generally runs 6,000 hours a year, but this is running 1,000 hours a year, then like multiplying by 6 seems like at least, I mean, it's certainly not like a great approach, but it seems better than just like a massive underestimation, right?
Right. Yeah. Yeah. Everything can be scaled up or down based on like knowledge of the fleet operator or from other sources. Um, and yeah, we can update the analysis results based on that.
Like, do you have any data on like averages or what's typical use of these sorts of data, even at more aggregated measures?
Yes, we do for the small sample that we have collected real world data from. And yeah, I should point out that this contract, this research project was run in parallel to another research project that collected data from close to 100 pieces of construction equipment. And then there's another research project that just started last year that will collect real world data, same type of data from a few hundred pieces of agricultural equipment. So yeah, in this particular project, we were only to use data from just 20 something pieces of equipment because that's what we had at the time. But now over time, I think our database has grown quite a bit. And yeah, we now have more than 100 pieces of real world data. 100 pieces of equipment with real world data.
Hope that answer your question, Colin. So the next one is from Thomas. Have any cost analysis scenarios been run with higher battery cost in the case supply became constrained? For example, battery usage overall is somewhat low currently. However, could the cost curve flip if the high demand outstrips supply? Also, everyone assumes battery supply will increase and keep up. Also, any analysis without incentives?
Yes, those are all interesting analyses. So in regards to battery cost, so yes, we did include that analysis as part of our overall sensitivity analysis. So here, aside from the base value assumption, we also simulate the case where the battery per unit cost increase or decrease by 10%. And yeah, in combination with the other changes in the other parameters, it can result in a range of cost analysis, cost effectiveness, as shown on this slide. And I agree that there will be a lot of more work to be done to understand how the surge in interest in EV would impact or affect the demand supply balance of battery price.
Right. Yeah, they're all really interesting questions. I hope we can answer them all. So next question is also from Colin. What does the cost of batteries mean in the context of the equipment? For example, 80K for a rubber tire loader's battery, isn't that similar to the cost of ICE equipment alone? For cost effectiveness, was that looking at the additional cost relative to the current price?
Yes, so that's correct. So we look at the difference between, okay. So yeah, we assume that if someone like CARB is to create an incentive program to fund the turnover of diesel equipment to electric equipment, the required amount of funding per unit of or per piece of equipment would be the difference between the EV component cost and the current component cost of diesel equipment. And yeah, with regards to the cost of the battery, it looked high again because of the data from the source that we use over project the battery price quite a bit. In reality, the battery price have come down a lot, and yeah, it should be just about half of what the projections show.
Right.
Oh,
So
sorry, real quick. Does the report include anything on like what the actual cost of that would be? Like, would it cost us like $500 billion to electrify equipment, or just something, or like a per equipment cost, something like that might be useful?
Yes, we do have the raw numbers in terms of the actual dollar amount per equipment, and that can be multiplied by number of equipment in specific types to arrive at the total dollars amount that would be required to electrify the whole category.
right, and the report will be available online as well. So the next question is from Patrick. Was any feasibility consideration given at the machine level for the mass of the required batteries versus mass of displaced ICE components?
Yes, yeah, that's a very good question too. And yeah, we did consider that towards the end. So at first, we did not account for the fact that the battery would be larger and heavier than fuel tanks. But yeah, we did a follow-on analysis. It's not part of the final report that will be released. But after the project, we did additional analysis to account for the fact that the battery will be larger. Now, our follow-on analysis focused on the weight, the increased weight of the battery electric equipment, and how it would actually impact the amount of energy required to move the equipment, right? Luckily, off-road equipment don't move a lot. Some of them do, but most of them don't move a lot as compared to cars. But there's still impact in terms of kinetic energy that is needed because of the increased battery weight. That is something that we are working on right now. But in terms of size, that is something we did not analyze in detail. We had some discussion around, okay, how can electric equipment be kind of packaged together, right, with the larger size of battery. In fact, yeah, there could be a case where the larger size and heavier battery can be used as counterweight for some of the equipment. So, and we have seen some real world example of very, very large electric equipment as shown in one of the earlier slides. So it's possible.
Hope that answered the question, Patrick. So the next question is from Michael. How does your analysis change when accounting for the value of LCFS credits that would be available for new electric off-road equipment types? He's curious that if this would increase the range of horsepower that become cost-effective, or were this incentive already factored into the analysis?
That's a good point. We have not factored in our LCFS credits, and you are right. If we do, then the larger equipment that consume more fuel would likely look more attractive, right, from the cost effectiveness perspective.
Okay. So the next question is from Alan. To what extent was input from engine and equipment makers included in your study here, both in the study design and in the collaboration section noted in the actual completion of the study?
Yeah, not much, as this study is fairly independent. Even though, yeah, we hope to have more inputs from the industry, and hopefully, yeah, we can refine the analysis to make it even more realistic. We did reach out to a few manufacturers, but did not get a lot of feedback. And I also should mention that as part of the study, CalSTART, which is on the research team, also conduct industry interview to understand the landscape of off-road electrification. And we have some feedback from that interview that is included in the final report, but yeah, I did not include it in this presentation.
Right. The next question is from Bruce. What was the assumed CO2 emissions per kilowatt hour of electricity? Power plant to plug?
We did not make that assumption. So the CO2 emissions that are used in the cost effectiveness analysis come from the Offload 2017 database. So right now we have not accounted for life cycle analysis. And yeah, it depends on the source of electricity generation. The CO2 emission per kilowatt hour will be different depending on the mix, the source mix.
Great. So the next question is from Zheng Hepan. When calculating the daily energy assumption, how was trip number determined? By using the NRTC time multiply with 4 times or from real world recorded data?
So everything is based on real world recorded data. The daily energy consumption, because we have the data on a second by second basis, that is also include timestamp, so we can sum up the amount of energy that would be required on a calendar day basis. And for the different calendar days in our data set, then we use the maximum daily energy consumption in the battery sizing analysis.
So the next question is from Danielle. Did you take into account the battery useness life?
No, yeah, we did not take into account that, but with the project duration of 10 years, so I think that can be considered as a soft consideration of battery life, because that's the typical warranty period.
Right. So there's some more comments. Thank you, Brian, for the comments. I don't see a question there. And also thank you, Colin, for the comments. And I think the next question was just from Bill Robertson. To what extent were more efficient powertrains and the flexibility of electrification assumed to contribute to reduce shift energy requirements? For instance, use of multiple motors or single versus single engine, digital displacement, hydraulics, multiple chamber cylinders, direct electric actuation. Sorry, I have to read everything for the audio purposes. So, and everyone else can actually see this in your own chat. The Bobcat BEV compact track loader is said to need a 6+ larger battery without this kind of improvements. So, Knok, can you answer the question?
Yes, so I'm not sure if this is in the context of energy consumption or cost effectiveness calculation. With regards to cost effectiveness calculation, we did include advanced engineering costs. So the need to redesign the powertrain to make electric equipment works, that is accounted for in the cost calculation.
Hope that answered your question, Bill. So I just put the online source here for everyone's information, and we're just going to go through the question, and if we need to go back to the main presentation, I can switch back. How were barriers to feasibility quantifying of equipment that would have to be redesigned to accommodate mass increases associated with full electric versus ICE? Question from Patrick.
Yeah, I think there are multiple layers of barriers. From the technical barriers, we did not dive deep into how the powertrain or the equipment need to be redesigned for that, or need to be engineered. We did include the advanced engineering cost in the cost effectiveness analysis, but that is the main focus of the analysis. Now, in terms of market barriers, I think yeah, those are something that still need to be further studied. There were a lot of comments earlier about how OEM in the off-road sector might compete or might be able to get batteries with a price that is in line with what on-road OEM might be able to get. So those are things that are not part of the study, but hopefully CARB will look into in the future.
Right. Yeah. Thank you for that comment and answers. I think that is the last question I see in the chat. And please raise your hand if I missed any of the questions. So I will just unmute you so you can ask a question. Okay, I'm not seeing any raised hand. And again, the presentation and final report will be available on the website showing here next week. So also the question from Alan, will CARB be considering alternative approaches for reducing emissions such as renewable diesel fuels? I think there are colleagues that are working on this, and it's not really on the scope of this research work. And if you have certain concerns or questions, you can always email me, and my email address is here. Oops. Actually, I will just type my email address. Oh, it's here on the last bullet point. And I will consult my colleagues, and I can always get back to you by email. Do we have any additional questions? Please raise your hand or type into the chat. And again, thank you so much, everyone, for coming. And thank you, Kanak, for the awesome presentations. I'm not seeing any additional questions. And we're really, oh, yeah, you're right. Okay, sorry. The email address is actually QI dot. I missed a dot here. So I'm going to send everyone in the chat my email address. And Kinok, if you want, you can also type your email address to the chat. Right. Again, thank you, everyone, and thank you for all the awesome questions. And we're trying to get back to you with additional questions and everything. So again, thank you, Kinok, for the presentation. And that'll be the end of the seminar. And thank you.
Thank you, everyone.
I'm going to stop it.